Welcome back to video notes about circuits. Today we're talking about parallel circuits, which are going to be a little different from series circuits. Here in parallel circuits, there is more than one path that the current can take. It can move through each of these loops separately. That means that different devices can be operated independently. This resistor or maybe this light bulb can still work even if this one in the middle isn't. As long as it isn't on the main line that the break is, the other pieces can still work. If there was a break right after the battery, then you're going to have some problems because this part goes to each of the different paths. But if the first resistor here was broken or not working, the other two could still work because they are on independent paths to the battery. So if one light bulb were to go out, the others would still stay lit because they have their own paths to the battery. Resistance is a little bit more complicated when it is in parallel or in a parallel circuit. The equivalent resistance will decrease as new branches are added. So this formula is going to be an important and kind of confusing one because 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. That is not the same as if it was 1 all over R1 plus R2 plus R3. You have to have each of them as separate fractions. So in order to calculate the total or equivalent resistance in parallel, you would add up the inverse of all of your resistors and then take the inverse again to have this RT by itself. So if R1, R2, and R3 were all 2, then I would have 1/2 plus 1/2 plus 1/2 to have 3 halves. So now I have 1 over total resistance is equal to 3 over 2. I can take the inverse or just flip both sides upside down to get the total resistance is 2 over 3. This is going to be where it gets confusing and tricky, in my opinion, but as long as you remember to keep each part separate, and then at the very end to flip everything, you'll be okay. Voltage in a parallel circuit, across each branch, the drop is going to be the same. Since each branch has its own connection to the battery, the voltage drop through each branch will be equal to the battery voltage. You have to look at each branch separately because there can be more than one resistor in each branch. If there is only one parallel set in the circuit, then the voltage drop will equal the battery voltage. If it's just a single loop with just a single light bulb, then the voltage drop across the light bulb will be equal to the battery voltage. But for each branch of a parallel circuit, each separate line that you can take, then the voltage drop will be the same as the battery voltage. That brings us to Kirchhoff's junction rule, which talks about current and how the current splits as it moves through the branches. Remember, with a series circuit, current was the same no matter where you were. With a parallel circuit, the current splits and breaks apart as it goes through different branches. So the sum of the current in the branches will equal the current in the main line. It's easiest for me to think about it as the current as soon as I leave the battery before I go into any branch is equal to the current in each of the branches added up. So at the very beginning, right after I leave the battery, I have a current of 3 amps. When I get to a branch point somewhere where it can split, I've got 1 amp going down to this light bulb, 2 amps keep moving forward. I have another branch point, I have another junction, 1 amp goes through this light bulb, 1 amp keeps moving forward. That does mean, and it's a little bit hidden by my toolbar here, but at the junction points on the other side, those amps are coming back together. So by the time I am entering the battery again, the current should be back to what it started as. Those this amp that cut straight across and this amp that went around came back together, and at this junction point down here, I should be back to 2 amps. Down after this branch, the third will be added back in, and you can kind of see that I've got a bigger arrow down here. I am back to having 3 amps going into the battery and coming out again. So the total current will be equal to all of the different branch currents added up. Here I've got 1, 1, 1. The total is 3. So I had 5 chickens starting right at the beginning in the main line. I get to a junction point. If this piece was not here, then all 5 would move from B to A and move around. Otherwise, I might have 2 go along this path, 3 go along this path. By the time they come back together, no matter how they move, I've got all 5 back here. So between points B and A, the total current doesn't change, but remember that some of them are just taking different paths to get there. So if I look at that with Ohm's law, if I put that together with my I is V over R, then the amount of current that goes through each branch, the individual current, is going to be inversely proportional to the resistance in that branch. Not the total resistance, just the resistance of that branch. More resistance means you're going to get less current. To find the current in a branch, that's where you use Ohm's law, just rearranged a little bit. The voltage is the voltage you get from the battery. The resistance is the resistance in that branch. And the little ones, the little subscripts, just mean we're talking about branch 1. If it was I2 equals V over R2, you're talking about branch 2. As long that's just to help you keep track of what piece of the parallel circuit you are looking at. That means the total current in the circuit you can find using Ohm's law for the entire circuit. The total current will be equal to the battery voltage divided by the total resistance. So now if I think about the electricity in your house, with the series circuits, I talked about how Christmas lights, if one light bulb is burnt out, then that means the entire string isn't going to work because that is in series. Homes, you might have realized, are probably wired in parallel circuits with lots of different appliances running at once. The total or the equivalent resistance drops and more current can run through the wires. It also means that if my kitchen light bulb were to go out, it does not affect my TV in the living room because one piece can break without it breaking the entire circuit. Extra current may create enough thermal energy or heat to melt the insulation on the wires, which could cause short circuits or fires. Some advantages of these parallel circuits is each outlet has its own path. One outlet can have something connected to it and turned on, while another outlet has nothing connected or something burnt out or turned off. Each outlet has its own path, and if one outlet short circuits and breaks, it doesn't necessarily mess with the other outlets. Every outlet is getting the same voltage because one side is connected to the same wire. I've got a parallel wiring here, so each one of these outlets is getting 120 volts. They're all connected to a safety grounding wire as well. But each one of them is getting the same voltage. If they were in series, remember they would each have a voltage drop as you move along the circuit. But since we are in parallel, the voltage is the same for all of them. Some disadvantage is that because the resistance has gone down, that means current has gone up. Remember, those are inversely proportional. So more current is running through the wires, which means it could overheat and could lead to electrical fires or short circuits. So a short circuit occurs when there is very low resistance, which means very large current, and the current takes the path of least resistance, and it can produce a lot of heat, which can then lead to a fire. So you imagine here, if I was used to 2 ohms resistance, then this would work fine. But if I have a path available where there is a very small resistance, you can see Ohm's law worked out here. That is a lot of current. That is a very large current, which is going to produce a lot of heat. This is not the same as an open or broken circuit. Open means that the path has been broken, and so current cannot flow at all. Short circuit, I've got a path of very, very low resistance where lots of current can flow through. There are a couple of ways you can prevent against that happening, like in your house, fuses and circuit breakers. Fuses will melt if the current passes through, if the current that passes through is too large, which then will open the circuit or make that path not usable anymore if the current is too large. Ground fault interrupters prevent any kind of dangerous shocks. So you might have noticed on outlets near your sinks, you've got another little reset or test button. It has the outlets near your sink have special things built in to prevent any kind of dangerous shocks or overloading. So here's an example of a fuse. This would just be along the wire in your circuit. And if the current that passes through is too large, the fuse in the middle will break and the current cannot pass through anymore. Circuit breakers work in a similar way. You probably have, maybe in your garage or in a basement somewhere, a circuit box or a breaker box where you've got circuit breakers for the entire house. And maybe you've had to go and reset, flip one if the power goes out. But these, you can open or close the circuit if the current is too large. If the current is too large, a lot of times these will just shut off completely. In a house I lived in once, if you ran more than 3 appliances in the kitchen, it would shut off and you would have to go into the basement and flip the breaker for that. So these will automatically turn off or open the circuit if the current is too large. And here we've got ground fault interrupters within your outlets. So that is it for parallel circuits and how the electricity in your house is wired. If you've got any questions, please feel free to reach out, and good luck. Have a good day. Bye.